All right. Hello and welcome everyone to my presentation on the basic proof of finite speed of propagation in one-dimensional degenerate Einstein-Brownian motion. My name is Bergeron and I'm from Kansas State University, and my advisors for this project were Akif Ibragimov and Isanka GarliHevage from Texas Tech University, and this project was created through an REU at Texas Tech, which was funded by the NSF. So to begin, our project was based on the classical Einstein model of Brownian motion for diffusion, where Einstein used the primary parameters of delta, tau, and phi delta, as defined here, and he used the whole universe axiom and the assumptions of the frequency of jumps being even, the expectation of jumps being 0 as in number 3, and then the Einstein conservation law, all to prove or all to derive the classical heat equation without the previous methods of anyone. And here in our project, Ux of t is going to be our solution, which represents the number of particles per unit volume. So to begin, we're going to go over some background information of the classical heat equation. So first, we have the weak maximum principle, which states that the maximum of U on the closure of the domain, as defined in 1.5, is equal to the maximum of U on the parabolic boundary, as defined in 1.6. Then we have our strong maximum principle, which states that if the maximum of U is attained at x naught t naught in the domain, then U is constant for all x and time before t naught. So in the non-degenerate or classical case of Brownian motion, when tau is constant, the strong maximum principle implies that the speed of propagation is infinite. So for our IVP 1.8, if g is greater than or equal to 0, g is greater than 0 for some x naught, then Ux of t is greater than 0 for all x and t greater than 0. So this is unrealistic to model many physical situations. So what we'd like to do is prove the finite speed of propagation so that we can more accurately model certain situations. So we have our degenerate case where tau is non-constant is our interest. And specifically where tau is equal to 1 minus alpha over u to the alpha, and alpha is between 0 and 1. So we want to show that this exhibits the finite speed of propagation property, which means that for u of x 0 greater than 0 on our domain, x minus x naught less than or equal to delta, and u of x 0 identically equal to 0 outside of this domain, then we would have u of s of t equal to 0 much further outside of this domain on our time domain between 0 and big T. So to derive our model, we first take our tau value and d naught equal to 1 and substitute it into our classical heat equation. Then we simplify to achieve 1.11. So this model represents nonlinear Brownian motion and is not guaranteed the strong maximum principle. So here's our project of interest, and we're going to let u be greater than 0 be our classical solution to this IVVP. So our goal is to prove that U preserves the strong maximum principle and thus has the finite speed of propagation property. So to begin, we're going to prove the weak maximum principle. So we do this by proving lemma 1, which states that if we let Wx of t be a generic function such that the inequality 1.16 is true for some t less than infinity, then Wx of t is less than or equal to the maximum Wx of t on the parabolic boundary. So to prove this, we assume that x naught t naught in our domain and Wx t naught is equal to the maximum W of x of t, where x of t or x and t are in our parabolic boundary. Then this implies that our first derivative of W to the 1 minus alpha with respect to t at x naught t naught is greater than 0, and then our second derivative of W with respect to x at x naught t naught is less than or equal to 0. Thus, as in 1.19, our inequality is greater than or equal to 0, but we assume that it would be less than 0. So we have a contradiction, thus proving our limit. Moving on, we introduce lemma 2. So if we assume for some generic Wx of t on omega t, then 1.2 is true. And if Ax of t is greater than or equal to 0, then Wx of t is less than or equal to the maximum Wx of t on our parabolic boundary. So the proof of this lemma is the same as lemma 1, so I won't go into this, but we are then going to use lemma 2 to prove our weak maximum principle, theorem 3. So if we let ux of t be our solution of the inequality 1.21 with 0 less than alpha, which is less than 1, and if ux of t is greater than or equal to 0, then ux of t is less than or equal to the maximum of ux of t over the parabolic boundary. So we prove this by first introducing the equation W epsilon equal to epsilon times the quantity big T minus T plus Ux of T, where the big T is constant and the other constants are defined as in 1.22. And also the maximum of our solution on the domain, on the closure of the domain is equal to U of X naught T naught, which is greater than 0. So to continue our proof, we first let Ax of t equal u to the minus alpha. Then we substitute in our definition of W epsilon, and then we simplify to achieve the right-hand side of 1.23 in the neighborhood of the point x naught t naught. Now we can use our lemma 2, and we know that W epsilon of x naught t naught is less than or equal to the maximum of W epsilon on the parabolic boundary. Then we can substitute in our definition of W epsilon to achieve 1.25. Next, we can subtract over our epsilon times the quantity t minus t term to the right side and simplify to achieve 1.27. Finally, we can take epsilon as it approaches 0 to achieve our desired inequality, 1.28, and we are done. Next, we're going to prove the strong maximum principle, but first we're going to introduce a new domain notation that is going to help us in our iterative inequalities to come. So if we look down here, we're going to let ln equal big L minus 2 to the negative n, where big L is constant, and in equal x such that 2l is greater than x, which is greater than ln. And finally, jn equals in minus in plus 1. And we're going to let xn be in jn minus 1 and cn be in jn minus 2. And just note, cn is less than xn. And so our domain is going to look like this diagram down here. This isn't drawn to scale, but this is where the points should be. So our first lemma is going to be showing that our function v of x, which equals the integral from 0 to t of ux tau d tau, satisfies the maximum principle as shown in 1.35. And just to note, this tau is a dummy variable for time. We are integrating with respect to time here. This is not the same tau. So to prove this, we first integrate 1.29, or our nonlinear heat equation, with respect to time to achieve 1.36. And then we use the fundamental theorem of calculus for 1.37. Moving on, we know by our initial values from our model that 1.38 is true. And so we can simplify to 1.39. Now, by assumption, we know that u is greater than or equal to 0, which implies that our second derivative of v with respect to x is also greater than or equal to 0 on our domain from L over 2 to 2L. So this implies that our first derivative of v with respect to x is increasing. However, we know from our boundary values that the first derivative of v with respect to x at 2L is equal to 0, and thus we know that our first derivative of v with respect to x is less than or equal to 0. So v is decreasing, and thus v of cn is greater than or equal to v of xn for cn less than or equal to xn. So now we have our new domain notation and our maximum principle, which we can then use to prove the strong maximum principle. So first we have lemma 5, which states that if ux of t is the solution to our IBVP 1.29 through 1.32, then the integral over in of u to the 1 minus alpha x t dx is less than or equal to 2 to the n plus 1 times the integral from 0 to t of u of ln minus 1 tau d tau. So to start this proof, we integrate with respect to t. We integrate equation 1.29 with respect to t as in the previous proof, and we get to the same point as 1.44 as in the previous proof. But now we integrate again with respect to x over part of in minus 1. So we integrate from xn to 2l to take advantage of the mean value theorem in a few steps. So then we take the absolute value of both sides, and we look at the right side for 1.46. We evaluate the integral, and then we know from our boundary values in 1.41 that our first derivative of v with respect to x at 2L is equal to 0, and we are left with the right-hand side, 1.46 here. Then we can apply our mean value theorem to achieve our final equation here. Moving on, we can use the property, this property of the absolute value to achieve 1.47. And then using our previously proven maximum principle v of x, we know 1.48 to be true. Finally, substituting in our definition of v of x, we can achieve the right-hand side of 1.49. And using this previously proven fact of 1.5, we can thus achieve our desired inequality here at the bottom. So now we have another iterative inequality. So the integral over in of u to the 1 minus alpha xt dx is less than or equal to 2 to the 2n times the integral from 0 to t times the integral over in minus 2 of ux tau dx d tau. So to prove this, we're going to first recall that Cn is less than ln minus 1. So then using our maximum principle of v of x, we know 1.52 to be true by replacing this point Cn. So then we can use the integral mean value theorem to show that 1.53 is true. We can then substitute in the definition of v of x and consolidate our constants to achieve 1.54. Moving on, we know that in minus 2 contains the region ln minus 2 to ln minus 1, so we know 1.55 to be true. Thus, we've shown that 1.56 and 1.57 are true, and we can consolidate these facts to show our desired inequality, 1.58. Moving on, we now have our main iterative inequality. So to show this, we first assume that u naught of x in 1.3 is such that ux of t is less than or equal to 1. Then if we let in tilde equal the maximum from 0 to t of tau of the integral over in of u to the 1 minus alpha x tau dx, then in tilde is less than or equal to 2 to the 3n minus 2 times c of alpha times t times in minus 3 tilde to the 1 plus epsilon power. And here we're going to have two cases where epsilon equals alpha over 1 minus alpha and c alpha equals 2l to the 1 minus 2 alpha over 1 minus alpha when alpha is less than 1/2 but greater than 0, and then epsilon equal 1, which equals c alpha when alpha is greater than to 1/2. So to prove this, we're first going to observe the fact 1.56 first to achieve this inequality, and then we can break up our u of ln minus 1 tau function to achieve 1.64. So then we can introduce the points Cn1 and Cn2 as shown, and using the maximum principle of v of x, we know 1.65 to be true. So then we can apply the mean value theorem to each function here on the right side and achieve 1.66 over their respective regions. Then we know that in minus 3 contains both the regions jn minus 2 and jn minus 3 by definition, so we know 1.67 to be true. Finally, we can consolidate our constants, and we know that the maximum over the region of an integral times the length of the interval is greater than or equal to the integral itself, so we know that 1.68 is true. Continuing, we take our first case when alpha is between 0 and 1/2, and we can observe that alpha over 1 minus alpha is between 0 and 1. So using our Holder inequality for the second integral of 1.68, go back, this integral here, we can then achieve the same integral, but instead we have u to the 1 minus alpha to the power alpha over 1 minus alpha. Then to achieve 1.69, we can consolidate these powers into the same integral, but to the 1 plus epsilon power, where epsilon is equal to alpha over 1 minus alpha, and c alpha equals 2l to the 1 minus 2 alpha over 1 minus alpha. Now we can take our second case when alpha is between or is greater than or equal to 1/2 but less than 1, and we know that alpha is greater than or equal to 1 minus alpha. So then in our second integral of the right-hand side of 1.68, we know that u to the alpha is less than or equal to u to the 1 minus alpha due to 1.59. So in 1.69, we have the same equation 1.69, except that epsilon is equal to 1 and c alpha is also equal to 1. So now that we have our finite speed of propagation, we can then achieve the localization property through the Lataszynskaya iterative lemma. So if we assume that our solution ux of t is such that I naught tilde is less than or equal to this constant, then in tilde of t approaches 0 as n approaches infinity. So our integral approaches 0. Thus, u to the 1 minus alpha x of t is identically 0, which implies that our ux of t is identically 0 over our time domain 0 to t and our x from L to 2L, where our above constants are the same as the previous theorem. This is the end of my presentation, and this research was supported by the REU NSF grant, number DMS 2050133. Here are my sources, and I look forward to any questions about my presentation. Thank you for watching.